So we've now come back inside and we've connected the Raven unit to the local Ethernet in the office where it's warm. And we'll show how to download the MCAP files, how to look at them, and then how to bring them into DeepView Enterprise. Once they're in DeepView Enterprise, the process brings in the file, performs initial auto annotation with a seed model. So the seed model that we're using currently is trained to detect people. So what we are expecting to happen and what we'll be showing is that after import, we've automatically generated 3D bounding boxes for all the people in the scene. So we'll review those, make sure there's no mistakes, nothing missing. If there are, we'll make those adjustments. And then from there, we'll show adding a new class and doing the 3D bounding box annotations on a new class that wasn't known yet. So in your typical workflow, you would do this, and then you would retrain that seed model, which is a model that runs in the cloud and is trained to detect whatever target objects you need for your particular use case. And then as you build up this data set, as you import new recordings, the model's now able to make those detections in pre-creating the 3D bounding box for you. So early on in the development process, you'll be doing a little bit more annotation of unique classes, and then that model trains over time, gets better and better, and then later on your workflow will be mostly automated and you're only having to audit the results. But now let's look at the MCAP files. So I'm on the Raven UI here from my PC. We can see these recordings we captured. Now typically the radar data cube will be recorded at a lower frame rate, say 1 frame per second. But for the purpose of these recordings, we've captured it at the full 18 frames per second. So these recordings, even though they're short, they're quite large. And most of that is from the radar data cube. Again, mainly for demonstration purposes. Typically your data set, 1 frame per second is more than enough. So we can click the info, the details here, and we can see the topics we captured. So there's the GPS. Camera info gives details of the camera, so resolution, the extrinsic profiles, and pixel to format. The LiDAR points is captured from the Ooster. We've got the camera, the actual video feed in H.264, the IMU, the radar data cube, so this is the low-level range Doppler cube. The radar targets, this is the higher level point cloud data. Radar info, again similar to camera info, just some specs on the radar, which configuration we used. And then TF static is the static transformation. So this carries the extrinsic profiles for the camera, the LiDAR, the radar, the way we've configured them so that we know how to reorient everything into a common viewpoint. And we'll see that when we look at it in Foxglove, how everything is all aligned. So I'll start by downloading the first recording here. I'll just click the download button. And it is 3 gigs, so it'll take a few moments. So while this is happening, we'll fast forward the recording so you don't have to wait for it. Now here I've opened up the first of the 2 recordings into Foxglove Studio, and I've prepared a layout already with a few common views. I'll lower these because we're not using them. So when you first load, you'll see a blank screen like this, and if we click play, we'll capture a couple frames and then we can pause it again. So in the top left, we have the LiDAR data along with the radar point cloud drawn, so in the 3D view that we can navigate around like this. And then below this view, we have the camera view from the Raven with the point clouds from the LiDAR and radar overlaid over the camera view so we can get this perspective view. In the top right, we've set up just the camera view so we get a clear view of the camera. And then we have the radar cube. So here we see this is with the drive grid 169 configured for 1 transmitter and 4 receivers. Now each of these radar cube contains 1 matrix per receiver, so we only show 1 receiver at a time so that we can see it clearly, and then if there were multiple transmitters we would show those here. So in another video we'll go over deeper dive of the radar data cube, but for now we'll just see this view. And then finally on the bottom right we've set up the GPS. Now by default it's showing the full path we traveled, so I'll click the settings and just adjust it, the history mode, to only show previous. So we'll see this GPS marker update as we're driving around. All the views are configurable. The radar cube, we can change the coloring scheme between rainbow, turbo. The camera view has some settings as well. The more interesting settings are in this 3D view where we've combined the camera, the LiDAR points, and the radar points or targets, so that they can all be drawn together. So if I click play now, speed it up a little bit to 2 times. We'll see as we drive around, we can see on the cube to the right side is as elements are approaching the camera, the radar. So as we're driving forward, all the main objects are approaching that way. As we turn, we can start to see this streaking there. That's items moving away from the radar. So otherwise, the radar cube's not too easy to reason with. We'll show some examples when people are walking around how we can kind of see where they appear on the radar cube. But what's important is that the low-level fusion model is able to interpret the data cube along with the camera to make predictions. We'll go over the results of the model at the end of the workflow tutorial. Here we see a really nice view of the train driving by and the effect that it has. I'll skip ahead slightly, and we see people here from when earlier in the video when we saw this. If I skip ahead a little further, as we're walking, we can see these markers here are the people. So Foxglove is a great tool for visualizing the MCAP recordings, and as we'll show in a later video when we deploy the model back onto the Raven, we can also record model outputs into the MCAP file so that when we review them in Foxglove we can see all of these results in here. But for now we'll move on to bringing the MCAP file into DeepView Enterprise, where we can create annotations and to train the model. Okay, next we'll be uploading the MCAP file into DeepView Enterprise. We'll show 2 parts to the import. One with the full automated ground truth generation, and what we're expecting to see there is once the MCAP upload is complete and the project is available in DeepView Enterprise, all the people should be all or entirely all annotated. This is done by using automated prompts into our annotation workflow. So people, there's a seed model that can detect people already. It can generate all those
annotations. Now you can also train your own seed model with your own use case specific data set, and then that model can generate prompts. So effectively you start to iterate on a data set where you start and you'll have no seed model. You'll start doing the annotations. The model starts being able to detect those target objects, and now when you import further MCAPs, they get automatically annotated. At first it'll make more mistakes and you'll have to make those corrections, and then as the data set grows, the model will get better and better at detecting the target objects up to the point where very few corrections are required, and that kind of gives you a good sense that your data set is now fairly complete. So let's see a few projects here. We'll be focusing on building this Raven medium range data set. So if we open it up, it is currently empty, and then we'll go and click this menu here, and then under data snapshots we can import the MCAP files, and then we'll be able to annotate them. So I'll go ahead and upload the MCAP files, and then we'll speed up the video and skip to the next step. Alright, so we've got our first file uploaded, and now we will import it as a data set. So in the first part we upload the MCAP into DeepView Enterprise, and in the second part we process it into a data set. So first it converts the MCAP into a data set format, and then can also run some automation steps. So we'll click the restore button. We'll select our medium range project. Depth generation. This runs a large depth estimation model which takes the camera image from the Raven and runs it against a model that's been calibrated for the Raven's camera optics, and generates a fairly accurate depth map. And this can be used for helping create 3D bounding boxes. Now in our case we did the capture paired with the LiDAR data, which gives far more accurate depth information. So we'll skip this step, but in cases where you've done recording without a LiDAR, then this depth generation step can be useful. The AI ground truth generation is the automated 2D bounding boxes, segmentation masks. Those are all performed in 2D on the image, and then from that we match the 2D bounding box to an object in 3D space using the LiDAR, or if we don't have the LiDAR, using the depth estimation. And then that's also combined with the radar data to generate really accurate 3D bounding boxes where we can now see where that object is with respect to the camera. So this is done automatically when we select this step here, and the bounding boxes are based on that seed model. So by default we provide a seed model that can detect people, but you can retrain your own seed model for whatever your specific use case might be. Now I'll call this dataset name yards, and then the date when we captured it. This is just a common convention that we use. So train yards, or rail yards, is where we were driving around, and then the date, but you can use whatever format you like. Now we'll click restore snapshot, and now that this is kicked off, if we switch back to our datasets view, we'll see here the yards 2025, February 14th, and this is being imported. There's a few steps to the process which will update these progress bars as it goes through, and then eventually will be complete and able to be visualized. So again, we'll skip ahead a little bit and then we'll dig into the imported dataset. Okay, so now that the import's complete, we can see we've imported 977 images, so that's at 1 frame per second. We've got one label, person, and one annotation set was created as part of the import. More annotation sets can be created either to separate types of objects that you're looking for that might not fit within one annotation set, or more commonly when running validation. So we could split up this annotation set is what was automatically generated, then we can create another one showing what was audited in case any corrections were needed, and then finally once a model is trained and we perform validation, it could be used to again annotate this same sequence, and then we can do comparisons between the initial automated annotations, the audited one, and the model generated ones. Now we'll open up the sequence, then we'll select this first one over here. Now in this view, by default, we see just the camera view. Go ahead and lower the frame rate to 1 FPS, which is how we imported it. And then we'll turn on the LiDAR view, which can be done by saying LiDAR point cloud, which opens up the 3D perspective. We can also turn on the radar point clouds, give us some additional points being generated by the radar. And then finally 3D bounding boxes, which will render the automatic bounding boxes that were generated during import. Now if we click play, we'll see it's driving around. I guess we can speed it up a little bit here. So we can see the driving around, the camera view, the LiDAR data, the radar point cloud is in there as well. And then as we approach here, we can slow it down a little bit. And then we'll see when we get out of the car, here we go, all the people have been automatically annotated already. So with no additional effort on the part of the user, we get automatic 3D bounding boxes, which can then be used to train the model. We can continue to play through here, make sure all the boxes look correct. You can see a few at the edge here are missed. They're out of the camera field of view. Now we've set up the LiDAR to over capture a wider field of view than the camera can see, and those areas could be annotated, but since they're out of the camera field of view, we'll ignore them. So this shows the automated ground truth generation, and this was performed on the 2 sequences. Now we can go back to our data snapshots. What we'll do this time is we'll import, but we will bring it into medium range, but we won't select either the depth or AI ground truth. And this will just be to show what the process of annotating from scratch would look like. So again, we'll call this yards. But we'll label it no automated ground truth generation. So now we'll restore this snapshot. Again, we can return to the datasets view, and we'll see this is now being imported. In this case, it won't generate the 3D bounding boxes, but will show going in there and what the manual annotation process looks like. And that really helps show the benefit you get from the automated ground truth. It saves a lot of time by having a data set that only needs some review. Now again, this works on examples where we already have a seed data set that can make good detections. So if we had to create a new one from scratch because we're adding a new class that's unknown, that's what we'll be showing now, what the workflow looks like when this is being done from scratch. So again, we'll skip ahead and then we'll go look at the video once the data set, once it's imported. Okay, so in the previous portion of the video, we showed importing with the AGTG enabled, so the automated ground truth generation, and we saw we automatically got the segmentation masks, 2D bounding boxes, and the 3D bounding boxes with respect to the LiDAR data, all automatically generated for people. And as we've seen in this, and we'll see in other videos, for if we have a good detection model to handle the automated prompt generation, then that all goes out and creates the 3D bounding boxes, and there's very little user effort. But that won't always be the case. So if you're adding a new class and you don't yet have a model to generate those prompts automatically, then at the beginning, the user, you will have to go create those by hand. Now there is quite a bit of automation around that, which is what we're going to be demonstrating right now. And then keeping in mind that as you build up this data set, you can generate, you can train a new detection prompt model, which will do basically the AGTG process, so that you don't need to go do this manual process here of creating the prompts around the target objects. The model that you've trained will run on the tool in the cloud and automatically handle that. And as I mentioned, as you build up the data set, at first you'll still need to do more corrections to it, but eventually that model gets really good, and it'll always find your target objects, or nearly always. And then there's very low effort to this data set effort. So let's go ahead and open up the sequence here, and I'll show what the process looks like. So we'll skip ahead to, let's show how this works. So under annotation sets, we have these annotations. This is like the ones we saw when they were automatically generated, except now they're empty. We have not yet created the annotations. We've created our label for person, which is what we're interested in annotating here. So I'll go ahead and click Edit Annotations. This switches to the Edit view. We can go ahead and open up the LiDAR viewpoint. And we can see that on the screen. Now I'll skip ahead. I've looked at this, so I know around frame 348 is when we first see a person. So I'm clicking in the middle here, and we can see already the person on the side here. They're just out of the field of view of the camera, but the LiDAR, which we've set up to have a wider field of view, we can see they're there, and they're about to enter the scene. And then we'll create one annotation. So I'll go ahead and click forward until they enter the scene. And now with this, we'll now go into the automated video segmentation tool. So we click this here. Pops up. So first we do need to initialize the state. I'm going to select my backend runner here and then initialize the state. And what this does is it prepares the model to process the video. Now in this case, I knew I'm only going to be dealing with the second half of the video, because before that we were driving around and there was no relevant objects. But you can initialize the state from the beginning of the video, from the end. I could change the end frame to only be, a small section of the video. And why you would do that is if there's only 10% of the video, a certain section where there's pieces that you want to go annotate, you can just focus on that. It speeds up this processing a little bit, though, it doesn't take too long. It takes about, I think, 15 seconds or so to set up this right here. There we go, it's ready to go. So we'll go ahead now and create the box annotations. There's actually two ways to do this. We can use points, or you can click the object. Kind of show it here, like this. And, in this case, it worked really well. Sometimes you might need to add a couple points to create. And we can see as I added more points on the jacket, it forced the model to kind of emphasize that which I was clicking. Personally, I prefer the box tool. I find it more intuitive. So I put the box around the person here. There we go. We get the mask, and that's basically it. At this point, we click propagate, and it'll go through, and we'll see after that it'll for this person, it'll get probably 90% of them throughout the video, and then we'll go fill in the blanks and add the other people, and after which it'll all be annotated. So under the hood, the automated ground truth generation on import, what it's doing is what I just did, that drawing that initial bounding box. That's what we call the prompt. So I've told the model I've got an object here that I want to have detected and tracked, and it will create if I click over here, I've just turned on the 3D bounding box, so now we see the 3D bounding box is right there on the LiDAR data. Yeah, it drives all that. So as I mentioned, if we don't have a prompt model yet, what the user needs to do is go through and create the prompts by hand. This data set we're generating, the 3D bounding boxes, we're hoping to use these for training the fusion model, for the spatial perception, but we are still generating 2D bounding boxes and these segmentation masks, and that can be used for training a cloud detection model that's then used for doing the automated prompts. So again, for the user, you can evolve over time for custom objects. We're going to be showing a lot of people through this workflow because we're specifically working on a pedestrian detection data set, but it really could be anything. Certainly for detection and segmentation, if you can see it, if you can tell it apart, the model should certainly be able to do that as well. This I'm referring to the Edge model that runs in real time on the Maven, providing segmentation masks and bounding boxes. The fusion model, we do depend on the radar being able to see certain things. So what I mean by that is we can detect people, we can detect cars, we can classify them, but if I wanted to say a model that can tell me if workers have hard hats on or safety vests, I can do that with the visual model through segmentation or detection of the vests and the hard hats, but the radar, it can't tell, right? The radar can't see a safety vest. So the radar would tell you there's a person there, and even with fusion, it's helping reinforce that there's a person there, but you would need to also train the vision model to say and they're wearing a safety vest. Now the good news is we can run both the fusion model and the segmentation and detection visual model both in real time in parallel on the Raven platform. Plus the Raven platform does also support additional NPU accelerators. So what we're showing there in real time is running in 2 tops, and we can support upwards of 26 tops on the device. So there is quite a bit more horsepower available. But now we can see it's completed the propagation step, so we can hit play. I'll lower the frame rate just a little bit. And now when I hit play, we'll see it's all annotated for this person. we have the 3D bounding box on the right side. It's tracking them nicely, as we see by the LiDAR data. And even on the edge of the screen there, it still tracks very well. So now we can save these pending segmentations, and now we'll add the next person that's entered over here. So let's back it up just a touch to see where they enter the scene. Okay, actually what I'll show, so let's go there. So well in the scene here, and show a neat feature. At the beginning we could see, the person was right on the edge. So the camera is going to have a hard time seeing it, but the radar does have a wider field of view, and there is some tolerance, much like the Fusion model can still detect people when the camera is obscured. We can detect people that are just outside the field of view of the camera. Now this is entirely dependent, of course, on the dataset being properly annotated like this, but that's part of why we overshoot the LiDAR data a bit, is so that we have, a little bit of annotations just on the edge of the camera's field of view. So I'll create the bounding box. There we go. But this time I'm going to select this option, which is reverse propagate. So what this does is, instead of going forward and tracking the person and generating all the segmentation masks and bounding boxes, it's going to run it backwards, and that'll get the early parts. So go ahead and start it. So it's done doing the back propagation now. So I'll go just back up a little bit here, and we can see it's created that annotation from earlier frames. So I can go change the frame rate. If I click play, there we go. And now, because it was backwards, it didn't do the forward one. So we'll go back. Yeah, so we have that one. So now we'll just do a normal forward pass. Bounding box. Oops. Bounding box. There we go. I missed a few. So this is where points can be handy. See, it kind of missed around the leg, so we can fill those in and we get a better mask. Perfect. So I'll turn off backwards, so it's normal, forward, click propagation, it'll go forward, and then that person will be done. We'll show that once it's done, and basically rinse and repeat for every object in the scene. Does take a little bit of effort, but kind of you get in a groove. You normally don't really need to do that backwards pass as well. That's was more to demonstrate, but it's rare that it's strictly needed. The auto importer will always do it because it's happening in the background and the user is not waiting for it. But this shows kind of the workflow where you're doing it so-called manually. I mean, it's still it's only partially manual in the sense that we have to go pick our objects, it tracks them across the video, generates the 3D bounding boxes, and does all of this automatically. And again, the purpose here is we're going to quickly get to a model that we can train and use as part of the auto import pipeline. So that portion, how you can customize the auto import pipeline, will be covered in a future video. Otherwise, for this video, we'll quickly show once the forward propagation is done here, and then otherwise we'll move on to the next video, which will be how to train the two models with this. So we'll be covering the Fusion model for the spatial perception, what these 3D bounding boxes are all about. We'll be training the detection segmentation model that's based on vision only, works on just a normal Maven, not only the Raven platform. It uses the camera to generate the effect we see on the left here, so the bounding boxes and segmentation masks. And finally, as I noted, we'll train actually a third model. This model is not for edge deployment. It actually just lives in DVE, and it's used as part of automating the import pipeline. So, next time you're importing objects into your data set, they get automatically annotated. So here's the propagations done. Click play again, and we see again the bounding boxes. So we'll repeat it for that person, and so on until we've completed the data set. As part of this video series, we'll be showing the building of this medium range pedestrian detection data set, basically from the ground up. There'll be clippets that show interesting parts in building the data set and how the model is evolving as we build up the data set. We'll also have just an overview of the training that uses a pre-built data set in ultra short range mode. And that's it. Thank you.